What if the most dangerous threat to a skyscraper is not an earthquake, a storm, or a fire, but a flaw so small that no one feels urgent enough to stop the project? A single steel beam, barely crooked, installed just a few millimeters out of alignment, became the silent trigger for one of the most devastating structural failures ever recorded. At first glance, nothing looked wrong. The building rose floor by floor, inspections were signed off, schedules were met, and confidence grew with every ton of steel lifted into place. Yet hidden inside the skeleton of the tower, a subtle geometric deviation was quietly rewriting the laws of load distribution. In large-scale construction, steel beams are designed to behave predictably. Their strength is not just in the material itself, but in their geometry. Straightness, alignment, and orientation determine how forces travel through the structure. When one beam deviates, even slightly, it does not simply weaken itself, it redirects stress into places never meant to carry it. In this case, the beam was not bent enough to be rejected by visual inspection. It was within what many would casually call an acceptable tolerance. That assumption would prove fatal. The beam arrived on site after a long journey from the fabrication plant. Somewhere between manufacturing, transport, and storage, it had developed a subtle curvature, not dramatic, not obvious, the kind of imperfection that experienced workers have seen hundreds of times before. Under pressure to keep the project moving, the decision was made to install it anyway. After all, steel is strong. The design had redundancy, and the deviation was small enough to correct later, or so everyone believed. Once installed, the beam behaved differently than the calculations predicted. Loads that should have flowed vertically began to shift laterally. Microstresses accumulated where connections met. Bolts compensated, welds absorbed more than their share. Nothing failed immediately, which reinforced the illusion that everything was fine. This is how structural disasters are born, not from sudden mistakes, but from quiet compromises that normalize risk. As the building climbed higher, the forces multiplied. Each additional floor increased the pressure on the distorted load path created by that single beam. The structure adapted, but adaptation is not safety, it is delay. Engineers rely on models, assumptions, and perfect geometry. When reality diverges, even slightly, the structure begins operating outside its intended behavior. No alarms sound, no dramatic warnings appear. Only subtle shifts, invisible to the naked eye, continue accumulating energy. Workers reported occasional noises, metallic pops, faint creaks, dismissed as normal settling. Minor adjustments were made elsewhere to compensate for misalignments that no one could fully explain. Each fix treated a symptom, never the cause. The beam remained where it was, quietly distorting the structural logic of the entire frame. The danger was not that the beam was weak. The danger was that it changed how the building understood gravity. By the time anyone seriously questioned the anomaly, the skyscraper was already committed to a path it could not escape. Removing the beam would mean delays, investigations, financial losses, and reputational damage. Leaving it in place felt easier, safer, more convenient. And that decision locked the structure into a countdown no one could see. Because in complex systems, failure does not announce itself loudly, it whispers. And once the first whisper is ignored, the rest follow faster than anyone expects. If this story is already making you question how fragile massive industrial structures can really be, I want you to pause for a moment and get involved. Understanding how disasters like this happen is not just about curiosity, it is about recognizing how small decisions can spiral into catastrophic consequences. Leave a comment below and tell me what you think was the most dangerous part of this situation so far. Was it the flawed beam itself, or the human decision to ignore it? Your perspective matters here. If you are finding this analysis valuable, make sure to hit the like button and subscribe to the channel so you do not miss the next part of this story. In the next section, we will dive deeper into how that single crooked steel beam made it past inspections and into the heart of the skyscraper. The story of this failure does not begin at the construction site. It begins months earlier, inside a steel fabrication facility where precision is assumed, not questioned. Structural beams for skyscrapers are manufactured under strict specifications. Length, cross-section, straightness, and residual stress are all tightly controlled because engineers design entire load paths around the assumption that these elements behave almost perfectly. But manufacturing is not a flawless process. Steel is heated, rolled, cooled, cut, and moved repeatedly, and each step introduces the possibility of subtle deformation. In this case, the beam left the factory already carrying a slight curvature. It was not dramatic enough to trigger rejection. Laser measurements showed values that hovered just inside the upper tolerance limits. On paper, it was still acceptable. In reality, that tolerance existed to account for minor imperfections in isolation, not to justify installing a compromised element into a system where precision stacking effects matter. The difference between allowed and safe is often misunderstood, and this beam lived exactly in that dangerous gray zone. Transportation made the problem worse. Long steel members experience uneven support during shipping. Temperature changes cause expansion and contraction. Vibration over hundreds of miles introduces microstresses that do not disappear when the truck stops. By the time the beam arrived on site, its curvature had increased slightly, but not enough to look alarming. To an experienced crew under scheduled pressure, it appeared workable, straight enough, good enough. On the construction site, inspection procedures focused on visible defects, surface damage, and connection points. The beam passed these checks. What inspectors did not evaluate in depth was how that curvature would interact with the rest of the frame once fully loaded. Site inspections are designed to confirm compliance, not to re-engineer the building in real time. That limitation creates blind spots, especially when deviations are subtle and distributed rather than obvious and localized. Installation sealed the mistake. As the beam was hoisted into position, workers noticed minor resistance during alignment. Bolts did not slide in as smoothly as expected. Hydraulic jacks were used to coax the connections into place. This was recorded as normal field adjustment. No escalation occurred. No red flags were raised. In complex construction, adjustments happen constantly, and notice problems only become problems if they stop progress. This one did not. Once fixed into the frame, the beam imposed its geometry on everything connected to it. Adjacent members compensated. Connections absorbed unexpected forces. The structure adapted silently. Engineers trust steel to redistribute loads, and steel did exactly that, just not in the way the design intended. The beam did not fail immediately because failure was not the goal of the system. Stability was, and stability can exist right up until the moment it suddenly does not. The most dangerous aspect of this stage was not the crooked beam itself, but how ordinary the situation felt. No alarms, no dramatic confrontation, just a sequence of small decisions that made sense locally but were catastrophic globally. Each person involved believed the system would absorb the imperfection. No one owned the responsibility to question whether the system should have been challenged instead. By the time that beam became structurally significant, removing it was no longer a realistic option. The building had grown around it. Loads were already flowing through altered paths. What began as a minor deviation had become a locked-in condition. From that moment on, the skyscraper was no longer the building that had been designed on paper. It was something else entirely, quietly carrying a flaw no one wanted to see. If this beam had been rejected at the factory, replaced during transport, or flagged during installation, the story would have ended here. But it was not. And that is what makes what happens next inevitable, rather than accidental. Before we continue, leave a comment and tell me what you think failed first in this stage: the manufacturing process, the inspection system, or human judgment under pressure. Modern skyscrapers are not built on intuition, they are built on mathematics. Every beam, column, and connection exists because an engineer calculated how forces would move through the structure under thousands of different scenarios: wind loads, dead loads, live loads, thermal expansion, dynamic movement. All of it is modeled with extreme precision. But inside those calculations lives a concept that is both necessary and dangerous: tolerance. Tolerances exist because perfect geometry does not exist in the real world. Steel is never perfectly straight. Concrete is never perfectly uniform. Bolts are never placed with absolute precision. Engineers know this, so they design structures that can absorb small deviations without failing. The problem begins when tolerance is misunderstood as permission rather than protection. In this skyscraper, the calculations assumed that any deviation would be random, isolated, and statistically insignificant. What they did not account for was a deviation that was directional, persistent, and locked into a critical load path. The crooked beam did not merely reduce capacity, it changed how forces traveled through the frame. Instead of flowing cleanly downward, loads began to shift sideways, introducing bending stresses where only axial forces were expected. On paper, the numbers still worked. Each individual component remained within its rated capacity. No single beam was overloaded. No connection exceeded its design limit. This created a false sense of security. Engineers reviewing partial data saw no obvious violation of safety margins. The system appeared stable because failure was not concentrated in one dramatic point. It was distributed quietly across dozens of connections, each absorbing a little more than intended. This is one of the most dangerous characteristics of structural failure. Engineers are trained to look for exceedance, stresses above limits, deflections beyond thresholds, factors of safety dropping below acceptable values. But progressive failures rarely announce themselves that way. Instead, they operate inside the margins, exploiting assumptions baked into the calculations themselves. The tolerance for beam straightness, for example, is typically defined for individual members, not for how multiple deviations interact when stacked vertically across dozens of floors. When one slightly crooked beam forces adjacent members to compensate, those compensations propagate upward and outward. Floors above inherit misalignments they did not create. Columns experience eccentric loading they were never designed to handle. Over time, the building stops behaving like a rigid system and starts behaving like a flexible, stressed organism. What made this situation worse was reliance on redundancy. Redundancy is supposed to save structures when something fails, but redundancy only works when loads are redistributed in predictable ways. Here, redistribution followed an unintended path. Redundant elements did not relieve stress, they accumulated it. Each backup quietly became part of the problem. Compounding this was the use of simplified models during construction stage reviews. Full finite element simulations are rarely rerun for minor field adjustments. They are expensive, time-consuming, and often seen as unnecessary once construction is underway. The assumption is that tolerances exist precisely to avoid the need for constant recalculation. In this case, that assumption became a blindfold. As the skyscraper rose higher, the effects of gravity magnified the error. Loads increased not linearly. Small misalignments at lower levels produced larger deflections above. The structure compensated by redistributing stress through connections never intended to serve that role. Bolts experienced shear instead of tension. Welds absorbed bending they were not designed for. Still, nothing snapped, nothing collapsed, and that was the most misleading signal of all. False confidence grew from silence. If the building were truly unsafe, someone believed, it would have shown clear signs by now. But structures do not behave like machines that fail suddenly when a part breaks. They behave like systems that tolerate abuse until one final condition removes their ability to adapt. The calculations were not wrong. They were incomplete. They assumed geometry that no longer existed. They assumed load paths that had been quietly rewritten. And once that assumption was violated, every safety factor built on top of it began eroding invisibly. By the time anyone considered revisiting the math, the structure had already committed to a new internal logic. A logic that no longer matched the drawings, no longer matched the models, and no longer matched the assumptions that justified confidence in the first place. At this stage, nothing had collapsed yet, but the building was no longer merely standing. It was surviving, and survival is not the same as safety. Long before a skyscraper collapses, it begins to communicate, not in dramatic failures or visible cracks, but in subtle signals that only matter if someone is willing to listen. In this case, the building started speaking early, and it spoke quietly enough that its warnings blended into the background noise of construction and occupation. The first signs were mechanical sounds, metallic pops, faint creaks, and irregular noises that occurred during temperature changes or periods of high wind. Steel structures expand and contract constantly, so these sounds were quickly classified as normal behavior. No single noise repeated often enough to seem urgent. No clear pattern emerged. Each sound was isolated, dismissed, and forgotten. That is how warnings disappear, not because they are ignored, but because they are explained away. As interior work progressed, alignment issues became more noticeable. Door frames required adjustment. Window panels needed shimming. Floors showed minor leveling discrepancies that exceeded what designers expected, but not enough to violate occupancy standards. Contractors corrected these issues locally, treating them as finishing imperfections rather than structural symptoms. Every correction made the building appear functional, even as the underlying imbalance remained untouched. Behind walls and ceilings, connections were working harder than intended. Bolts experienced microslippage. Welds absorbed cyclical stresses that accelerated fatigue. None of this triggered alarms. Structural health monitoring systems, if present at all, were not calibrated to detect slow, distributed anomalies. They were designed to catch sudden events, not long-term distortions, developing under everyday loads. One particularly telling signal was load redistribution during wind events. Engineers reviewing sensor data noticed that certain columns responded more aggressively to lateral forces than predicted by the model. The explanation offered was wind variability and modeling uncertainty. After all, wind is chaotic. Models are approximations. The numbers were close enough to justify confidence, close enough to avoid deeper investigation. Maintenance reports added another layer of quiet evidence. Minor cracks appeared in non-structural elements. Ceiling tiles shifted. Expansion joints behaved unevenly. Each issue was logged, repaired, and closed. None of them pointed directly to a structural defect, and that was the problem. Disasters rarely announce themselves with a single obvious cause. They reveal themselves through patterns that only become visible in hindsight. At the core of the issue was normalization. Every industry develops a sense of what is acceptable. When minor anomalies appear repeatedly without immediate consequence, they stop being treated as anomalies at all. They become part of the environment. The building was still standing. People were still working inside it. Inspections continued to pass. That ongoing success created trust that the structure was fundamentally sound. But the structure was adapting, not stabilizing. Each adjustment shifted stress slightly, forcing the system to find new equilibrium. Over time, that equilibrium became more fragile. The building relied increasingly on components that were never intended to carry critical loads. Redundancy turned into dependency. Flexibility turned into vulnerability. What made this phase so dangerous was that intervention still seemed possible, but unjustified. To stop and investigate would mean acknowledging a problem without clear evidence. It would mean disrupting schedules, budgets, and reputations based on discomfort rather than proof. High-stakes construction, discomfort rarely wins against momentum. The building continued to speak, not loudly, not urgently, but consistently. Every sound, every misalignment, every unexplained adjustment was part of a message that no one assembled into a complete picture. Each specialist saw only a fragment. No one saw the whole. By the time those fragments aligned into something undeniable, the structure had already crossed a threshold. The point where listening could have changed the outcome had passed. What remained was a system still standing, still functioning, and already too compromised to save. Once the crooked beam altered the internal logic of the skyscraper, the failure was no longer localized. It began to spread silently, not as a crack racing through steel, but as a slow reprogramming of how the building carried its own weight. This is where the disaster became inevitable. Not because something broke, but because everything kept working just well enough to hide the damage. In a properly designed structure, loads follow clear, intentional paths. Gravity moves downward through columns. Lateral forces flow through bracing systems and shear cores. Every element knows its role. When that single beam sat slightly out of axis, it disrupted that clarity. Loads entering the beam were no longer centered. They arrived with eccentricity, introducing bending moments that were never part of the original design. That bending did not stop at the beam itself. It transferred into adjacent connections, then into neighboring columns, then upward into floors above. Each element compensated by taking on a fraction of the unexpected stress. No single component failed, because no single component was asked to carry everything at once. This is what made the failure so difficult to detect. The damage was distributed, not concentrated. As floors were added, the imbalance intensified. Steel does not forget stress, it accumulates it. Microscopic deformations formed. At connection points, especially where bolts and welds experienced alternating forces. Over time, these micro-deformations changed stiffness ratios across the frame. Some areas became slightly more rigid, others became more flexible. That uneven stiffness created new load paths that engineers never modeled. The building began behaving less like a unified structure and more like a chain of interdependent compromises. One overloaded connection pushed force into another. That connection responded by shifting load again. This cascading redistribution is known as progressive structural drift. It does not require a crack or a snap. It only requires imbalance and time. One of the most dangerous aspects of this phase was how redundancy backfired. Redundant systems are meant to provide backup when something fails. But here, redundancy masked the problem. Instead of one clear failure triggering intervention, multiple systems shared the burden just enough to prevent immediate collapse. Each backup element became part of the failure mechanism itself. As stresses migrated, certain columns began carrying loads slightly off-center. Eccentric loading introduced secondary moments that increased with height. Wind events amplified these effects. Thermal expansion added cyclic stress. The building flexed in ways that were technically within limits, but structurally unhealthy. Think of it like a body compensating for an injured joint. The pain moves, the damage spreads. At this point, even removing the original crooked beam would not have solved the problem. The structure had adapted around it. Load paths had been rewritten. Components had aged under conditions they were never meant to experience. The system had reached a new equilibrium, one that depended on continuous compromise. Disturbing it could trigger sudden failure. This is why catastrophic collapses often appear sudden, even though the damage develops over years. The structure is not slowly falling apart. It is slowly balancing on a narrower and narrower margin. When that margin disappears, the collapse is rapid, violent, and irreversible. The dominoes were already falling. They just had not hit the ground yet. By the time the structural imbalance had fully embedded itself into the skyscraper, the problem was no longer purely technical. It had become human. Every major industrial disaster reaches a point where physics and psychology intersect, and this was that moment. Engineers, supervisors, project managers, and executives were no longer dealing with a crooked beam. They were dealing with consequences. At this stage, the warning signs were no longer isolated. Reports existed. Data existed. Inconsistencies had been noticed, discussed in meetings, and quietly deprioritized. But none of those signals came with certainty. They came with ambiguity. And ambiguity is where pressure thrives. Admitting a structural concern at this point would not mean adjusting a beam or correcting an alignment. It would mean halting operations, reopening calculations, and potentially exposing a flaw buried deep within the building's core. The cost would be staggering. Delays would ripple outward. Contracts would be challenged. Reputations built over decades could collapse faster than steel. This is where decision-making becomes distorted, not because people are careless, but because they are trapped. Engineers are trained to rely on data, but here the data did not scream failure. It whispered possibility. Managers are trained to manage risk, but this risk could not be quantified cleanly. It lived in probabilities, assumptions, and worst-case scenarios that no one wanted to own. Meetings focused on surface explanations, environmental factors, construction tolerances, normal material behavior. Each explanation reduced urgency without resolving the underlying issue. When one department raised concerns, another offered reassurance. Responsibility diffused across teams until no single person felt empowered to stop the machine. There was also a dangerous reliance on precedent. Similar buildings had stood for decades. Steel structures had absorbed imperfections before. Nothing like this had ever caused a collapse, at least not one widely remembered. That historical comfort became a shield against action. If it has not failed before, why would it fail now? But precedent is a poor substitute for understanding. Each structure is unique. Each configuration creates its own vulnerabilities. The crooked beam did not exist in isolation. It existed within a specific geometry, a specific load pattern, a specific sequence of decisions. Comparing it to past successes was comforting, but irrelevant. As pressure mounted, silence became strategy. Raising alarms without certainty was seen as reckless. Staying quiet felt responsible. This is one of the most lethal dynamics in engineering failures. The absence of proof becomes proof of absence, and by the time proof arrives, it arrives violently. What no one wanted to acknowledge was that safety margins had already been spent. The building was no longer operating with reserve capacity. It was operating on borrowed time. Every additional load, every wind event, every thermal cycle chipped away at stability. But stopping now felt worse than continuing. In hindsight, this was the final window for intervention. Expensive, embarrassing, painful, but possible. Instead, momentum won. The project moved forward, not because everyone believed it was safe, but because no one could justify being the one to say it was not. At that point, the collapse was no longer a question of if, only when. Before we continue, leave a comment and tell me this. Do you think catastrophic failures happen more often because of technical mistakes, or because people hesitate to act when the risks become uncomfortable? When the collapse finally began, it did not start where anyone expected. There was no dramatic explosion, no single beam snapping in half, no visible warning seconds before disaster. The failure started deep inside the structure, at a connection that had been quietly overstressed for years, carrying loads it was never designed to see. On that day, conditions were unremarkable. No record-breaking wind, no earthquake, no fire, just a combination of normal gravity loads, mild lateral movement, and thermal expansion acting on a system that had already exhausted its ability to adapt. The skyscraper had survived worse conditions before, which made what happened next so shocking. At a critical juncture near the mid-level floors, one connection reached its limit. Not the original crooked beam itself, but a neighboring element that had absorbed redirected stress for too long. Microfractures that had formed over countless load cycles finally linked together. The steel did not shatter, it yielded, and in yielding, it changed the geometry of the frame in a fraction of a second. That tiny deformation was enough. Once the geometry shifted, loads that had been marginally balanced were suddenly free to move. Columns experienced sudden eccentric loading. Floors above lost lateral support. What had been a slow, invisible problem became a fast, unstoppable process. The collapse propagated upward and downward almost simultaneously. Above the failure point, floors lost their support and began to drop, transferring enormous dynamic loads to the structure below. Below it, columns buckled as they were hit by forces far beyond their design capacity. This was not a pancake collapse in the simple sense. It was a progressive structural failure driven by loss of equilibrium. Within seconds, redundancy vanished. Elements that had quietly shared the load were overwhelmed all at once. The building's internal logic collapsed before the exterior followed. To observers outside, it looked sudden. To the structure, it was the inevitable release of years of accumulated imbalance. Engineers later calculated that, once the first critical connection failed, the remaining structure had less than 2 seconds to respond. No system, no matter how well designed, can adapt that fast under dynamic overload. The skyscraper did not fall because steel is weak. It fell because steel was forced to behave in ways it was never meant to. The most unsettling part is this: even at the moment of collapse, nothing technically went wrong in the way people expect. Materials performed as physics dictates. Connections failed. When overloaded, gravity did what gravity always does. The disaster was not caused by a sudden mistake, but by the final consequence of many earlier ones. This is why the collapse felt almost unreal to those who witnessed it. A building that had stood solid and silent for years disappeared in moments, not because something new happened, but because something old finally caught up. Once the first critical failure released the stored imbalance inside the structure, there was no mechanism left to slow it down. Skyscrapers are designed with redundancy, not with recovery. They can tolerate damage, redistribute loads, and adapt to change, but only while equilibrium exists. The moment equilibrium vanished, the collapse became a physical certainty rather than a structural problem. As the upper floors began to fall, the forces involved multiplied instantly. Static loads turned into dynamic impacts. Each descending floor struck the one below with energy far greater than its own weight, transferring shock through columns and connections that were already compromised. The structure below had no time to absorb or redirect that force. It was never meant to. This is where systems that once provided safety became irrelevant. Fireproofing, bracing, secondary load paths, none of them mattered anymore. Progressive collapse does not negotiate, it overwhelms. The lower levels experienced loads several times higher than their maximum design capacity in fractions of a second. Columns buckled, not gradually, but violently. Connections tore apart. Floors lost lateral restraint and folded inward. From the outside, the collapse appeared almost symmetrical, which confused many observers. Symmetry suggests planning or external attack. In reality, symmetry can emerge naturally when failure propagates through a uniform structural grid. Once the central load-bearing system failed, gravity followed the path of least resistance straight downward. The building was not pulled apart, it was pulled through itself. Attempts to intervene were meaningless. Alarms sounded only after failure had begun. Evacuation systems existed, but time did not. Once the collapse initiated, no human response could change the outcome. The structure transitioned from a standing building to a falling mass in seconds. That speed is what made the event so devastating. As debris impacted the ground, secondary failures followed. Adjacent structures suffered damage from falling steel and concrete. Underground systems collapsed under the sudden load. What began as an internal structural flaw expanded outward into an urban-scale disaster. Emergency response teams were forced to react to consequences, not prevent causes. In post-collapse analysis, engineers found no single element that could have stopped the progression once it began. Every potential arrest mechanism depended on components that had already been compromised by years of redistributed stress. The collapse was not a chain reaction that could have been interrupted. It was a release, sudden, complete, and irreversible. This is the cruel reality of industrial failures at this scale. The window for prevention exists early, when the problem feels small and manageable. Once that window closes, the physics take over, and physics does not pause for debate. In the aftermath of the collapse, the narrative shifted from shock to explanation. Investigators arrived with a single question: how could a modern skyscraper, designed with advanced modeling and multiple safety layers, fail under ordinary conditions? What they uncovered was far more unsettling than a single defective component. The forensic analysis began at the debris field. Engineers traced deformation patterns in twisted steel, fractured connections, and displaced columns. What stood out was consistency. Damage signatures pointed not to an explosive failure or a sudden overload, but to long-term stress redistribution. The structure had been weakening quietly, exactly as the models predicted. Once the altered load paths were reconstructed, attention returned to the crooked beam. Measurements confirmed that its deviation alone was not enough to cause collapse. That finding confused early media reports, but investigators were not looking for a smoking gun. They were mapping a chain of dependency. The beam had acted as the initiator, not the executioner. Its presence had forced the structure to operate under assumptions that were no longer true. One of the most uncomfortable discoveries involved documentation. Inspection reports showed no falsification. Calculations were performed correctly based on the data available at the time. Maintenance logs were thorough. In isolation, every step looked reasonable. The failure lived in the gaps between disciplines, where manufacturing tolerance met construction pressure, where engineering models met human judgment, where responsibility blurred across organizational lines. Investigators identified a critical cultural issue. The system was optimized for compliance, not challenge. Procedures ensured boxes were checked, not assumptions questioned. Once the beam passed tolerance limits on paper, it became invisible to deeper scrutiny. No protocol required re-evaluating global behavior when local deviations accumulated. Another disturbing truth was how long the structure survived in a compromised state. The building did not collapse because it was unsafe from day one. It collapsed because it aged faster than anyone realized. Fatigue, creep, and cyclic loading accelerated degradation at stressed connections. The structure consumed its own safety margins quietly, year after year. Public reports initially focused on the beam because it was tangible, but internal findings emphasized something else entirely. The collapse was a systems failure. Technology worked, materials behaved as expected. The failure occurred in decision-making frameworks that underestimated how small deviations can interact over time. Perhaps the most sobering conclusion was this: no regulation had been technically violated, codes were followed, standards were met, and yet the building still fell. That realization forced a painful reckoning within the engineering community. If compliance is not enough, then safety demands something deeper: skepticism, integration, and the courage to pause progress when uncertainty appears. The collapse did not just destroy a skyscraper, dismantled long-held assumptions about how modern structures fail, and more importantly, how they are allowed to survive long enough to fail catastrophically. In the months that followed, the engineering community was forced to confront a truth that was deeply uncomfortable. This disaster was not the result of outdated technology or reckless design. It was the result of confidence. Codes were rewritten, not because they were wrong, but because they were incomplete. New guidelines began, emphasizing global structural behavior rather than isolated component compliance. Engineers were encouraged, and in some jurisdictions required, to reassess entire load paths when deviations accumulated, even if each deviation remained technically within tolerance. The idea that acceptable always equals safe was quietly retired. Inspection protocols evolved as well. Visual checks and box-ticking procedures were no longer considered sufficient for complex structures. Advanced monitoring systems gained importance, capable of detecting long-term stiffness changes, unusual load redistribution, and early fatigue patterns. The goal shifted from catching failures to catching behaviors that lead to failure. Perhaps the most significant change was cultural. Engineering education began to focus more heavily on systems thinking. Students were taught that disasters rarely come from single mistakes, but from interactions between small, reasonable decisions made in isolation. Manufacturing, transportation, construction, and operation were no longer treated as separate phases, but as a continuous chain where responsibility never truly ends. The story of the crooked beam became a case study, not because the beam was unique, but because it was ordinary. That was the warning. Catastrophic failures do not require dramatic errors. They only require enough small ones to align. The beam was not the villain. The silence around it was. Even today, similar conditions exist in buildings around the world. Structures that stand, function, and inspire confidence, while quietly adapting to imperfections no one wants to confront. The lesson is not that skyscrapers are unsafe. The lesson is that safety is not static. It must be questioned continuously, especially when everything appears to be working. This collapse changed how engineers think about responsibility, uncertainty, and humility in design. It reminded an entire industry that physics does not negotiate, that materials do not care about deadlines, and that structures remember every compromise made along the way. And that is the most unsettling legacy of all. The knowledge that the most dangerous failures are not caused by what we ignore, but by what we believe cannot possibly go wrong. If you stayed until the end of this story, it means you understand how fragile even the most advanced industrial structures can be when small decisions go unquestioned. If this analysis changed the way you look at engineering, safety, or responsibility, take a moment to engage. Subscribe to the channel so you do not miss future deep dives into industrial disasters and hidden structural failures. Leave a like if this story made you think differently about how collapses really happen. And in the comments, write "small errors matter" so I know you watched all the way through. The next video is already on your screen, and it reveals another disaster where a detail everyone ignored changed everything. Click it now and keep going.